start on section 7.2. What page is this, Pat? Does anyone know what page this is?
It's 503.
Page 503. Okay, in this sort of second hour, what I want to look at is determine the eigenvalues of particular matrices. I'll tell you which ones they are: triangular matrices and diagonal matrices. How much is it easy to find those the eigenvalues of those matrices? Prove some properties, and let's have a look at the if we get time. Have a look at the Cayley-Hamilton theorem. Can't guarantee we will have time to do that, but I'll go as far as that. Remember, one of the reason why the Cayley-Hamilton theorem is important is because what's one of the most tedious problems in linear algebra? Yep.
Is that the inverse?
Yeah, finding the inverse. Yeah, you're trying to find the inverse of a 2 by 2 is okay, but 3 by 3 or any bigger is really tedious. I don't want to do it, and you find Cayley-Hamilton makes it a lot easier. If you use Cayley-Hamilton, you can find the inverse much easier than trying to find all those cofactors and everything else. Yeah. Okay, we'll do that later. Maybe we'll have to do that on Thursday, but we'll try to do it today if we can. So I'll come back to and the other thing is that Cayley-Hamilton helps in is work out the powers. So if you've got a matrix, even if you've got a 2 by 2, if you've got an A is equal to, I don't know, let's say 1, 2, 3, 4, and I said work out A10, you know, if I said find A10, you know, A10, you don't want to do 1, 2, 3, 4 times 1, 2, 3, 4 times 1, 2, 3, 4 times 1, 2, 3, 4. You don't want 10 copies of that. That's too. Everyone in this room will get it wrong. Okay, we're bound not to get that right, okay? And you'll find with Cayley-Hamilton, you can make life a lot easier. This is the way to do it. Use Cayley-Hamilton, or something we do later on as well, diagonalization. There's two ways of doing this, but I'll come back to why we need all these eigenvalues, eigenvectors in later on, maybe Thursday. I did say eigenvalues, eigenvectors came in pairs, and I said mother and baby, or mother and child, but that's really the wrong analogy. What's wrong with that analogy? What's wrong with saying the eigenvalue is the mother and the child of the baby is the eigenvector? Which makes sense because the eigenvector is produced out of the eigenvalue, so we know it makes sense. But one way it's wrong to say that. Why is it wrong? Okay, that's true as well. No, some other reason why it's totally wrong to say that. I'll give you a clue. The chalk and cheese. They're two different beasts. That's why the mother and child analogy is not really suitable. And the first is it's okay because you get the idea that you can find the eigenvalue. You can find the mother first, then you find the child. But in many ways, it doesn't work. Come on, hurry up, sit down. Why the chalk and cheese? What's an eigenvalue? Sorry? It's a number, it's a scalar, isn't it? What's an eigenvector? It's a vector, isn't it? That's why the chalk and cheese. Okay? One is a scalar, the other one is a vector. That's why so the analogy between mother and child is not quite right. Think about it, because simply because, you know, you're you talk about chalk and cheese, two different aspects. Okay, remember what the characteristic equation, we can write down, we say the characteristic equation is given by det A minus lambda I is equal to, that's how we find it, don't we? Yeah. What do we, when we solve this, what do we get? Can you face this way? Turn around, face this way. What do we get if we solve this? What do you end up with? When we solve it, in general terms, say you had a 4 by 4, what would you get? Sorry? If you got 4 by 4 or a 3 by 3, what would you get? Would you get a matrix? What? Go on.
Well, you get like a number.
Well, yeah, so you get a number as well, but what else do you get? Number is what you find at the end. What do you get out of this?
And
One's
then,
equal to,
is it like a long equation or something?
it's an equation, isn't it? That's what you get an equation, don't you? Yeah. For a 4 by 4, you'll get an equation of degree 4, wouldn't you? Yeah? For a 3 by 3, you're going to a cubic equation. Okay. For a 5 by 5, you get a quintic equation. Okay. So what you end up getting is really something like, you know, I don't know, lambda. It's a 10 by 10, lambda 10 plus 3 lambda 9 plus 6 lambda 7 and so on, all the way equal to 0. That's what you get, don't you? Yeah. Then you're going to solve this. You normally got to solve this equation, don't you? Yeah. Normally you're going to factorize it out and find the lambda values. Okay. So we call this p lambda, not this one, but in general p lambda. We say p lambda is called. Let's do n by n. So cn lambda n plus cn minus 1 lambda n minus 1 plus all the way plus c1 lambda plus c naught. Okay. That's called a characteristic polynomial. Okay, that one is a characteristic polynomial. We call that p lambda. What's the characteristic equation then? That's a polynomial. Okay, what's going to be a characteristic equation? What does it need to form that from a polynomial into an equation? Because at the moment you can't solve it, can you? You equal something, isn't it? Yeah. In this case, we say it's equal to 0. You change that equal to 0, and you get an equation, don't you? You call that a polynomial equation. So how many roots does p lambda equal to 0 have? How many roots does it have? Say if you've got an equation of degree 10, how many roots is it going to have? 10, yeah, exactly. 10, exactly 10 roots. What about if it's a cubic polynomial, equation of degree 3? How many roots is it going to have? Sorry? 3. And what about a quartic equation of degree 4? How many roots is it going to have? 4. And a quintic, an equation of degree 5 will have exactly 5 roots, yeah? But how do you know this? I'm going to tell you that. How do you know that? It's good guesswork. How do you know it's going to have exactly 5 roots for a quintic equation? Exactly 10 roots for an equation of degree 10. How do you know that? Well, you don't. Okay? You don't really know it at the moment because you wouldn't have done it very much. There's something called the fundamental theorem of algebra. Okay? What it says, if you have an nth degree polynomial equation, okay, nth degree, you have exactly n roots. You have exactly n roots. And it's a very difficult proof. You will not be able to prove it until you do complex analysis in the final year. Okay, I can't prove it to you now. You need a whole lot of complex analysis to prove that nth degree equation has exactly n roots. I mean, Gauss, like I say, one of the 3 greatest mathematicians of all time, he proved that for his PhD. That's what he did, and he found errors of other people like Euler and so on. Other people made mistakes in proving this, and he found their errors, and he actually proved it. And it's supposed to be one of the greatest PhDs ever in the field of mathematics. Okay, if you look at Gauss's PhD, it was to prove the fundamental theorem of algebra, which says for an nth degree polynomial, you have exactly n roots. Okay, so let's here's some examples. Here we are. Okay. So you got an equation of degree 5 there, so it'll have 5 roots, yeah, okay. Equation of degree 12, it'll have 12 roots. Equation a degree of 101 roots, yeah. But they may not all be different. They may not all be different. For example, let's take the 101. You might end up by solve this equation: x minus 1 to the power 101 is equal to 0. Yeah, you might have that, yeah. So all the roots are what? 101 of those, yeah. Okay, they may repeated roots, and when you get repeated roots, we say for eigenvector, we say we got, so for eigenvalues eigenvector, if you've got this, if you have for eigenvalues, you get this lambda minus 1 cubed, lambda minus 2 is equal to 0. What are your eigenvalues? What are your eigenvalues? Yeah, lambda equals 1, lambda 2 equals 1, lambda 3 equals 1, and lambda 4 equals 2. Yeah, you've got 4 roots. It's an equation of degree 4, isn't it? Yeah, if you expand that, you get an equation of degree 4. So you have 4 roots. Of course, there's your 2 distinct ones. We know that, 1 and 2, but these are repeated, aren't they? We sometimes in compact notation, we write this. In compact notation, we write this as lambda 1, 2, and 3 is equal to 1. Okay? And we call that got a multiplicity, that eigenvalue has a multiplicity of 3. Okay? We say this eigenvalue has a multiplicity of 3, and we call this one a simple eigenvalue. Okay? If it's only got, you know, only a linear form, okay, only 1 root there, we call that a simple eigenvalue. If it's got more than 1 root, okay, repeated roots, then we call it, if it occurs 10 times, then we say that eigenvalue has got a multiplicity of how many times? Like this one here, if lambda minus 1, 101, would have a multiplicity of 101. Okay? That's the terms we tend to use. Okay, let's do determine the eigenvalues and eigenspaces. That means so let's determine the eigenvalues and eigenspaces of this matrix. So let me write it down. Let's find the eigenvalues, and then we'll find the eigenspaces as well. So we've got A is equal to, what is it? 2, 1, 3, 2, 1, 3, 0, 2, 0, 0, 0, 2. Yeah? How do we find the eigenvalues of that matrix? Yep.
First, we need to get to the determinant.
Yeah, yep. We have det. We have det A minus lambda I is equal to what? What's equal in this case?
So that's going to,
sorry?
there's going to be that.
Yeah.
There's going to be 2.
Yeah.
Minus lambda.
Yeah, that's right. You just take away lambda on the diagonal. Yeah, 2 minus lambda. Yep, go ahead.
Then 1.
1.
3.
3, that's right. Yep.
0.
0.
2 minus lambda.
2 minus lambda.
0.
0.
0.
0. 0.
2 minus lambda.
Lambda, yeah. So all you do is take away the lambda along the leading diagonal, yeah? That's what it comes down to, doesn't it? Yeah? Now, what about this one? Where would you expand this one? Sorry? First column, or first column is okay? Or the middle row, yeah? I like the middle row, yeah, so go. Yeah, hang on, I haven't done that. I haven't proven this. I haven't proven that. I've got to prove that before I do what sort of matrix this is. Let's do it the long way, then you'll appreciate it. If I do it the long way first, then you'll say, hang on, I could have done this easier, although you wouldn't appreciate it.
I'm just going to say that because it's one of those triangular ones.
No, just Rachel just said that.
Yeah.
I don't want you to use that. I don't want you to use that theorem at the moment. I know what we're going to get. Oh, I see. Sorry. I was thinking of something else. Yeah, it's okay. No, you can say that. Sorry, I was thinking of something else. You're producing a result that I want to prove. Yeah, it's a triangular matrix. So what's the determinant of this going to equal? Yes, sorry, you could say that. Sorry, that we did that one. Yeah, I didn't realise. No, there was something else. I thought you were going to say we know what the eigenvalues are, which you will know in a second anyway.
Well,
if you expand that all out, what did you get? Rachel and Petra said 2. It's a triangular matrix. What's the determinant of a triangular matrix? Yeah, it's sorry. No, it's not. It's diagonal. It's something to do with diagonal. Yeah.
So you then do 2 minus lambda.
Yeah.
2 minus lambda.
Yeah. 2 minus lambda. 2 minus lambda is equal to 0, isn't it? Because it's a triangular matrix, isn't it? Yeah. Okay. So you got lambda 1, 2, 3 is equal to what? It's got
2.
2. Yeah. It's got the eigenvalues. It's got 3 eigenvalues. Lambda 1, 2, and 3. It's got a multiplicity of 3, hasn't it? Yeah. Okay. Now, how do we find the eigenvector corresponding to this? Let u equal x, y, z belong to lambda 1, 2, 3 is equal to 2. How do we find this? Go ahead. Yeah, exactly. And so we have we have, what is it? A minus, this time it's 2i, isn't it? Yeah? U is equal to 0. Okay? So we have A is the matrix, there it is. A is that one matrix, isn't it? Yeah? So what do you do? What's A minus 2i? What's it going to be? What do we get? You should do it top of your head. You can do a long way if you want. Yeah, it's going to be, take away 2 there, isn't it? Take away 2, take away 2. So 0, 0, 0, isn't it? Yeah? So you're going to 0, 1, 3, 0, 0, 0, 0, 0, 0, isn't it? Yeah? So you're going to get, so what you end up with is 0, 1, 3, okay? 0, 0, 0, 0, 0, 0, x, y, z is equal to 0, 0, 0. Yeah? Okay? So, the bottom two rows are useless to you, aren't they? What does it say? They're 0 is equal to 0. You know that. You don't need matrix theory to, or eigenvalue arguments to do this. What if you expand the top row? What do you get? If you expand the top row, what do you get? Yeah, y plus 3z is equal to 0. Yeah? Okay? So y is equal to minus 3z. So what do we have? What could z be?
Well, it could be anything.
Anything, any apart from 0, yeah?
Yeah.
Exactly. Let z equal s, where s is not 0, yeah? S is not 0. But what about, okay, so then y, what's y equal to? Then, yeah, minus 3z, which means it's minus 3s, isn't it, yeah? It's minus 3s. What about x? What can x be? Any number apart from 0. Well, it could be 0. They both can't be 0. X, okay, can be any number, can't it? Yeah, any number. Let x equal t. Yeah, let x equal t. Okay, so then we have x equal t. Then we have our what do you call it? We have our vector u is equal to x, y, z. Yeah. So what do we get? Yeah, t, x is t, there it is, look, t, the y is minus 3s, yep, and z is s, yeah? How can you rewrite this in vector form? Well, it's in vector form already, but,
you can
yeah.
rewrite it as, you can rewrite it in the s out front.
Okay, s, what do we get? If we get s, what do we get?
Then we get 0,
0,
minus 3,
yeah,
1,
1,
and then we get plus 2.
Plus t.
Yeah.
Yeah, go ahead, yeah, plus
Then
t.
you get 1,
1, 0, 0, yeah. What condition do you need? So this is your eigenvector, okay, or your eigenspace in a way, okay, for E2. But what about S and T?
They could be any number apart from 0.
Yeah, they both can't be 0. One of them could be 0,
Oh.
but they both can't be 0, yeah?
Okay, yeah.
Both S and T cannot be 0. Both
Okay,
S
then.
and T cannot
Okay.
be 0. Well, what if they are both 0? What happens then? Say S is 0, T is 0. What do you end up with? Sorry? No, what did you say? Yeah, you end up with a 0 vector, don't you? Okay? You end up U is the 0 vector. And remember, for eigenvector, it can't be a 0 vector. Yeah? So that's why you can't have both. You can have one of them as 0, but you can't have both of them as 0. Okay? You can't have S and T both 0. If they're both 0, then you'll find U is equal to 0. Yeah?
So when you said, well, S can't be 0.
Yeah, I mean, it could be 0. You're right. It could be. It's possible. Hang on. I'll tell you what. Let's do it that way, shall we?
It's fair for me to say.
Yeah. It is fair. Okay. They're both. S could be 0. Could in this case.
Yes.
But as long as T is non-zero, then okay.
Yeah.
So you could choose S as 0 and T is non-zero.
Yeah.
Then it'll be okay. All right. And this is. And if you look at this is so E2. So our eigenspace E2. If you just plot the eigenspace E2. Is really E2 because it's the eigenvalue which it belongs to, you know, okay? That's the eigenvalue was 2 for this. If you go back, look, the eigenvalue was 2. There it is, isn't it? Yeah? That's why it's E2. E2 is equal to really the set of vectors S is equal to 0 minus 3 1, okay, and plus t 1 0 0, okay, that's those set of vectors, isn't it? Yeah, okay, provided s and t are not both 0. And if you have to plot them, if you plot them in R3, I've done this in, I don't know, autograph or whatever it's called, okay, this is what you get. This is what you get. You get vectors, you get a plane. This time you don't get a line, you get a plane. Everything on that plane is, what do you call it, is an eigenvector. Everything on that plane is an eigenvector from the 0 vector. Okay? And the basis for that, what would an axis be for this? What would be an axis for this space? Say if you're asked to find the basis of your eigenspace. What does basis mean? What does the word basis, what does it actually mean? Come on. We've done bases, and you know you've got to tie all this up. You know, there's no good doing something at the beginning and not tying it up at the end. We've talked about basis or basis vectors throughout the whole course. What do you mean by basis? What are bases? For let's take R2 or R3. What do you need for R2 and R3? You need some vectors, but what else do you need? Axes, yeah, these are axes, aren't they? Okay, bases, axes, okay. You've got your XY coordinate, your normal axes, your normal natural axes, okay, your natural bases, but you can have your non-standard bases, can't you, okay? And this, for this space, if I asked you to find the basis, a basis for this would be this, okay? 0 minus 3, 1, and 1, 0, 0. It's really given by this, those two, okay? A basis for that is this. Okay, let's, where have I put that pen? Let's have a look at eigenvalues of diagonal and triangular matrices. This is what I thought Rachel and